Example 1, for all positive integers, show that 1 into 2 into 3 plus 2 into 3 into 4 plus 3 into 4 into 5, uh, so on n into n plus 1 into n plus 2 is equal to n times n plus 1 times n plus 2 times n plus 3 divided by 4. Now to show that, to show above the result for all positive integers, we use mathematical induction. First we are going to show that result is true for n equal to 1. So on the left hand side, LHS contains 1 into 2 into 3, which is equal to 6. On the right hand side, put n is equal to 1. This is the right hand side, so here put n equal to 1. So this is 1 into 2 into 3 into 4 divided by 4. So if you cancel this, it is equal to again 6. So LHS is equal to RHS. This implies result true for n is equal to 1. Now next, in step number 2, here we assume, assume that result is true for n is equal to k, that is 1 into 2 into 3 plus 2 into 3 into 4 plus dot 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 k into k plus 1 k plus 2 is equal to k into k plus 1 k plus 2 k plus 3 divided by 4. So we assume here step number 2. Now in the step number 3, we want to show that result is true for n is equal to k plus 1. So now consider here step number 3. For show that result is true for n is equal to k plus 1. That is, we want to show that that is in this equation we want to put here n is equal to k plus 1. So this will be equal to, that is we want to show here 1 into 2 into 3 plus 2 into 3 into 4 plus k into k plus 1 k plus 2, not k plus 1, sorry, we want to put n is equal to k plus 1. So this will be equal to k plus 1 k plus 2 k plus 3 is equal to k plus 1 k plus 2 is equal to k plus 1 k plus 2 k plus 3 k plus 4 divided by 4. So in this equation we put n is equal to k plus 1. Here we put n is equal to k plus 1. So this is k plus 1 k plus 2 k plus 3, here k plus 1 k plus 2 k plus 3 k plus 4 divided by 4. Now to show this, we consider LHS. So on the LHS it is 1 into 2 into 3 plus 2 into 3 into 4 plus k plus 1 k plus 2 k plus 3. Now we can write this is equal to, now the term before this term is, we can write this is 1 into 2 into 3 plus 2 into 3 into 4 plus term behind this term is k into k plus 1 k plus 2 plus next term is k plus 1 k plus 2 k plus 3. Now by using step number 2, the value of this term, by using step number 2, here is the step number 2. Now in the step number 2, the value of this term is k into k plus 1 k plus 2 divided by the value of this term is equal to k into k plus 1, k plus 2, k plus 3 divided by 4 plus k plus 1, k plus 2, k plus 3. So if you simplify this, multiply this 4 to this side, so multiply this 4 to this side, so denominator becomes same, so this will be equal to k into k plus 1, k plus 2, k plus 3 plus 4 times k plus 1, k plus 2, k plus 3, and this whole term is divided by 4. Now simplify the numerator. Now on the numerator there are 3 common terms, so take it outside, k plus 1, k plus 2 and k plus 3. If you take these 3 terms outside, inside the bracket it is k plus 4 divided by 4, and this is nothing but the RHS. This is what we want to show here. This is what we want to show. You can see here, this is what we want to show. So this is equal to RHS, and hence this implies the given result is true for n is equal to k plus 1, and hence by using mathematical induction plus principle we can say that result is true for using mathematical induction first principle of mathematical induction result hold for true for every positive integer or every positive integer. Now example number 2, for all positive integers, again for every positive integers we want to show that 1 into 1 factorial is equal to 1 into 1 factorial plus 2 into 2 factorial plus n into n factorial is equal to n plus 1 factorial minus 1. We want to check one more time, is it true? N plus 1 factorial minus 1. Okay, this is what we want to show here. Now again, to show this result for every positive integers, again like a previous example we are going to apply first principle of mathematical induction. So step first, show that result is true for n is equal to 1. So for n equal to 1, the LHS is equal to 1 into 1 factorial, it is equal to 1 into 1, which is equal to 1. On RHS, this will be equal to 1 plus 1 factorial minus 1. So this is equal to 2 factorial minus 1, which is equal to 2 minus 1 is equal to 1. So LHS is equal to RHS. This implies result true for n equal to 1. Now step number 2, we assume here result hold for n is equal to k. That is, we want to show that that is not show that, we assume that here, that is, sorry, we not show that here, we assume here result is true for n equal to k. So in this equation put n equal to k, so this is equal to 1 into 1 factorial plus 2 into 2 factorial plus n into n factorial is equal k into k factorial, k into k factorial is equal to k plus 1 factorial minus 1. Okay, we assume here. Now the step number 3 is very important. Step number 3, in this step we want to show that result is true for n is equal to k plus 1. That is, we want to show that 1 into 1 factorial plus 2 into 2 factorial plus, put n equal to k plus 1, so k plus 1 into k plus 1 factorial is equal to k plus 2 factorial plus 2 factorial minus 1. Now to show this, again consider LHS, and from LHS show that LHS is equal to RHS. So on the LHS it is 1 into 1 factorial plus 2 into 2 factorial plus k plus 1 into k plus 1 factorial. Now term before this k plus 1 into k plus 1 factorial is, we can write this is equal to 1 into 1 factorial 2 into 2 factorial plus k into k factorial plus k plus 1 into k plus 1 factorial. Now the value of this term by using step number 2, up to this, the value of this term using step number 2, here is the step number 2, is k plus 1 factorial minus 1 plus k plus 1 k plus 1 factorial. Now from these two term, that is this term and from this term, you can take k plus 1 factorial outside. So if you take k plus 1 factorial outside, inside the term, inside the bracket, it is 1 plus k plus 1 minus 1, this minus 1 as it is. So if you simplify this is equal to k plus 1 factorial into k plus 2 minus 1, and we know that this is equal to k plus 2 factorial minus 1, since we know that 3 factorial into 4 is nothing but the 3 into 2 into 1 into 4, that is, it is equal to 4 factorial. So same thing, k plus 1 into k plus 1 factorial into k plus 2 is k plus 2 factorial minus 1, and this is what we want to show here, which is what RHS, and hence result is true for n is equal to true for n equal to, again you can write by using mathematical induction, above result is true for all positive integers. Now next, example number 3. Example number 3 here, for all positive integer 1 into 2 raised to 1, 2 into 2 raised to 2, 1 into 2 raised to 1 plus 2 into 2 raised to 2 plus 3 into 2 raised to 3 plus dot 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 n into 2 raised to n is equal to n into 2 raised to n minus 1, 2 raised to n plus 1, n minus 1 into 2 raised to n plus 1, 2 raised to n plus 1 plus 2. Now again, to prove this, we are going to use mathematical induction. So step first, for n is equal to 1, again for n equal to 1, LHS is 1 into 2 raised to 1, which is equal to 2. on right hand side, this will be equal to 1 minus 1 into 2 raised to 1 plus 1 plus 2. So this term is 0. So 0 plus 2 is equal to 2. So you can see here LHS is equal to RHS. Now step number 2, we assume, and here you can write result is true for n equal to 1. Here we assume for n is equal to k. Assume that our result is true for n equal to k, that is 1 into 2 raised to 1 plus 2 into 2 raised to 2 plus 3 into 2 raised to 3 plus k into 2 raised to k is equal to k minus 1 2 raised to k plus 1 plus 2. So we assume this. Now want to prove this. We want now in step number 3, show that result is true for n is equal to k plus 1. Now this is inductive step. It is very important for n equal to k plus 1. That is, in this equation put n equal to k plus 1. So this will be equal to, that is we want to show here, we want to show that 1 into 2 raised to 1 plus 2 into 2 raised to 2 plus 3 into 2 raised to 3 plus k plus 1 into 2 raised to k plus 1 is equal to, now put here k plus 1. So this k plus 1 minus 1, that is k into 2 raised to k plus 2, k into 2 raised to k plus 2 plus 2. So this is what we want to show here. Now again the same technique we are going to use. Consider the LHS, and from LHS show that LHS is equal to RHS. So LHS is 1 into 2 plus 2 into 2 plus 3 into 2 raised to 3 plus, now the term behind this term, before this term, is k into 2 raised to k plus k plus 1 into 2 raised to k plus 1. Now by using step number 2, that is you can see here, this is the step number 2. By using step number 2, the value of this term is k minus 1 2 raised to k plus 1 plus 2 plus, now this term as it is, k plus 1 2 raised to k plus 1. Now k plus 1, sorry. Now from the first and last term, from this term and this term, okay, you can take 2 raised to k plus 1 outside. So what is left inside the bracket? It is k inside the bracket is k minus 1 plus k plus 1 and this plus 2 as it is. So this plus 1 minus 1 will get cancelled here, and this is equal to 2 raised to k plus 1 into twice k plus 2. Now we can write this as k into this twice k is 2 raised to 1 into 2 raised to k plus 1 plus 2. We know that a raised to m, a raised to n is equal to a raised to m plus n. So by using this formula, we can write this 2 raised to 1 as 2 raised to 1, 2 as 2 raised to 1. So this is k, and this 2 raised to 1 and 2 raised to k plus 1 can be written as 2 raised to k plus 2 plus 2. So this is equal to k into 2 raised to k plus 2 plus 2, and this is what we want to show here. This is what k into 2 raised to, you can see here, this is what we want to show, k into 2 raised to k plus 2 plus 2. This is equal to RHS, and hence by using mathematical induction, result is true for n is equal to k plus 1, and hence the result by mathematical induction, result is true for every positive integers. Now next, the last example, example number 4. Example number 4. The example is 1 minus 2 raised to 2 into 1 minus 3 raised to 2, 1 minus 1 upon 1 divided by 2 raised to 2, 1 minus 1 upon 2 raised to 3, 1 minus 1 upon n square, 1 minus 1 upon n square, not, this is equal to 3 raised to 2, not 2 raised to 3. This is equal to 3 raised to 2 is equal to, the value of this term is equal to n plus 1 divided by twice n. Again, want to show this for all positive integers. Again, we are going to use the same technique. Apply the mathematical induction. Step 1, for n is equal to, show that result is true for n is equal to 1. So on the left hand side, this will be equal to 1 minus 1 upon 2 raised to 2. So this is equal to 1 minus 1 upon 4. This is equal to, if you simplify this is 4 minus 1 divided by 4. So this is equal to 3 by 4. On the right hand side, put n equal to 1. So this is n plus n equal to 1. In this example, the base step is n equal to 2, not n equal to 1, n equal to 2, since it start from 2, and so base step is 2. So on this side we want to put n equal to 2. This is equal to 2 plus 1 divided by 4. So this is equal to 3 by 4. Now here base step is, in this example, here base step is n equal to than equal to 2. So assume, start your result from n equal to 2. So instead of 1 we write n equal to 2. Now step number 2, assume for result is true for n equal to k. This result is true for n equal to k. So 1 minus 1 upon 2 raised to 2, 1 minus 1 upon 3 raised to 2, 1 minus 1 upon k square is equal to k plus 1 divided by twice k. Now by using step number 2 and 1, show that result is true for n equal to k plus 1. So in step number 3, for show that result is true for n equal to k plus 1. So that is we want to show here, to show that result is true for that, put n equal to k plus 1. So it is 1 minus 1 upon 2 raised to 2, 1 minus 1 upon 3 raised to 2, 1 minus 1 upon k plus 1 raised to 2 is equal to k plus 2 divided by 2 times k plus 1. This is what we want to show. Now again, to show this k plus 2, show this, we are going to consider the LHS. So consider the LHS. On the LHS it is 1 minus 1 upon 2 raised to 2, 1 minus 1 upon 3 raised to 2, 1 minus 1 upon k plus 1 raised to 2. Now the term before this term is, this is equal to 1 minus 1 upon 2 raised to 2, 1 minus 1 divided by 3 raised to 2, 1 minus 1 divided by k raised to 2, and this term as it is 1 minus 1 divided by k plus 1 raised to 2. Now by using step number 2, the value of this term, by using step number 2, here is the step number 2. Now see here, the value of this term is k plus, sorry, value of this term, see here, this is the k step number 2. So value of this term, this is equal to k plus 1 divided by twice k. By using step number 2, k plus 1 divided by twice k into 1 minus 1 divided by k plus 1 bracket square. Now simplify this. To simplify this, take LCM here, so it is k plus 1 divided by twice k into k plus 1 bracket square minus 1 divided by k plus 1 bracket square. Now this k plus 1 and 1k plus 1 will get cancelled here, and if you simplify the numerator, on the numerator this is equal to k square plus twice k plus 1 minus 1 divided by, on the denominator this is equal to twice k plus 1. Now this 1 get cancelled here, we simplify this square term, so this is equal to k square plus twice k divided by 2 times k into k plus 1. Now simplify this is equal to, if you take k outside, from the numerator we get k plus 2 divided by 2 times k into k plus 1. Now cancel this k from numerator and denominator, we get k plus 2 divided by k plus 1, 2 times k plus 1. So this is, check whether it is, yes, this is what RHS, k plus 2 divided by 2 times k plus 1. So this is equal to what? RHS, and hence implies result is true for n is equal to k plus 1, and hence by using mathematical induction result is true for every n belongs to z plus using mathematical induction.